Good morning, everyone. Today, I'm going to explain chapter 4, Newton's laws explaining motion. Right. Let me share PowerPoint here. This one is chapter 4, Newton's laws explaining motion. Yeah. I'm going to explain this chapter. Before this chapter, I'm going to give some review previously studied. And for example, if we, I think in the beginning of class, I think there is we study usually mechanics deal with object motion. It will be classified into kinematics, dynamics, and statics. Kinematics deal with displacement, and velocity and acceleration. Dynamics is deal with force, and this is like we're gonna deal with Newton's second law, MA. And statics is equilibrium. Okay. Actually, previously until chapter 3, we studied only kinematics. It means we don't care about why the object is moving with constant acceleration. Yeah, just why. But is in this chapter, we're gonna see the reason for moving an object is just that is because of force applied to the object. Yeah, that is chapter 4. Okay, gonna see the slide here, and it has 5 sections there. First section is a brief history, and second is Newton's first and second laws, and the third one is mass and weight. Number 4 is Newton's third law. Number 5, application of Newton's laws. Okay, brief history. First, maybe ancient people thought why an object would move. And then Aristotle is one of famous philosophers, ancient philosophers and scientists. His viewpoint is like that. He believed that a force had to act for an object to move, and that the velocity of the object was proportional to the strength of the force. If we apply strong force, maybe its velocity will be, it depends on applied force. But sometimes even we don't apply force, it can keep moving. Yeah. What about that? I think if I throw stone, no, thrown rock is flying there. Even I stopped to apply force that this rock is keep moving. But in this case, he thought that there is something like air resistance keep pushing the rock. Aristotle thought like that. Then a heavy object would fall more quickly toward the earth than a lighter object because there was a larger force pulling the object to the earth. Yeah, actually, we learned acceleration due to gravity. Even big object and heavy object and lighter object is moving with the same acceleration. That is acceleration due to gravity, right? We learned this one, but he didn't know that. And aware of the resistance, a rock falls more rapidly through air than through the water. And she did not make a quantitative prediction that checked by experiment. After the picture air rushing around the thrown object to continue pushing the object forward, like this one, what I explained, like rock is thrown, rock, even we stop the force, but rock keep moving, right? When you throw rock, you must push the rock, and then rock initially gains some speed. Then it keep moving without, even I stop the force, the applied force, but keep moving. But in this case, he explained after the picture, the air rushing around the thrown object to continue pushing the object forward, right? It was wrong. And Galileo challenged Aristotle's view. Galileo Galilei, this Italian physicist, argued that the natural tendency of a moving object is to continue moving. No force is required to maintain the motion. He developed a mathematical description of motion that includes the acceleration d equal to 1 over at squared. I think we learned this formula in chapter 3 here. This formula is originally given by Galileo. Yeah, Galileo. Then here is Newton there. Yeah, I like Newton. He's very genius, and he developed physics as well as mathematics, or actually calculus. I think heard about calculus. Calculus developed by Isaac Newton. Actually, while he was studying physics, he needed to solve some problem, but he couldn't solve because of lack of tools there. Then he eventually developed new field of study that is calculus. Yeah, calculus developed by Isaac Newton. Anyway, what Newton accomplished, building on the work of Galileo, Isaac Newton proposed a theory of causes of motion that could explain the motion of any object, the motion of ordinary objects such as a ball or chair, as well as the motion of heavenly bodies such as the moon and the planets. Actually, here's during the pandemic, we already experienced the pandemic season, and actually we were quarantining home, but during the pandemic, Isaac Newton had to work from home he used the time wisely, right? And then he developed his 3 laws of motion in 1665, but when he was only 22 years old, 23 years old, right? And in 1687, I think even he developed this law that he didn't just expose, he kept withheld. But in 1687, about 45 years old, he formally published his ideas in Mathematical Principle of Natural Philosophy, Philosophiae Naturalis Principia Mathematica in Latin. This I think known as Principia. Yeah, Principia is very famous book. And here you're gonna see Newton's first law and second law. Newton's first law of motion is like this: an object remains at rest or in uniform motion in a straight line unless it is compelled to change by an externally imposed force. If an object is there is no any force acting on there, if it was at rest, keep rest. Rest means velocity v naught, that it keep the rest. T second letter, keep rest. If F equal to acting force, it's 0. But if an object is keep moving, V equal to 3 meters per second, and then if there is no any force, net force acting on the object, in that case, this one is keep moving with 3 meters per second. 3 meters per second. Then what happens if I have a text on the table like this text there? I push it, then this gained maybe V equal to 3 meters per second. They keep moving, then eventually it was stopped. Why stopped? Because there is a friction there, right? Friction is acting on there. Friction opposing the motion is not, in this F is not equal to 0, right? That make decelerate there, right? Here is a diagram. If F equal to 0, V remains equal to at rest, or V equal to V same velocity. V remains constant uniform motion in a straight line. And second law is Newton's second law of motion. The acceleration of an object is directly proportional to the magnitude of imposed force and inverse proportional to the mass of an object. The acceleration is the same direction as that of imposed force. A is the acceleration, F is net force, is the total or net force acting on the object, and M is the mass of the object. If I write it, maybe explain about Newton's first and second laws. I'm going to explain second law. That if I apply the force up here, like the force, that its mass is m. Then it's what about its acceleration? It will be accelerate if I apply force accelerate, but its acceleration depends on force, just the proportional force. If I the stronger force applied to the higher acceleration object gains, right? This if I have 100 Newton force applied there, that this is can make 200 Newton, then more acceleration. In this A equal to 10 meter per second squared, but 200 Newton applied to A equal to 20 meter per second squared, like that. Now, obviously, if you apply stronger force, that this accelerates more. But another thing is related to mass. Mass is just amount of object, right? Mass is really heavy, guys. If you have two object here, maybe if you see maybe same object, like there is a small, this is a ping pong ball, and another is a bowling ball. You apply the same force, 100 Newton, but this gained about maybe 200 meter per second squared, but bowling ball gained only 20 meter per second squared. Depends on mass. This mass is big, this is mass small. The acceleration will be inverse proportional mass. Mass is big, it's hard to move the object, right? You know, actually, this small boy and big boy, there is a if even you have same force, but it's a small boy is move more, but big boy is very slight move, right? That is if I summarize this one, A equal to F divided by M. But in this case, force might not be one force. Force can be multiple force can apply. Here is 100 Newton. Another is there is a friction force is 10 Newton. In this case, we have the total net force. If net force will be this 100 will be positive, then minus 10 Newton, that is 9 Newton, right? This case, we have to subtract this one. Yeah. But if I have maybe same direction is 100 Newton, 10 Newton applied there. In this case, total net force will be 100 plus 10. It's 110 Newton. 110 Newton, yeah. You have to consider this case. We're going to write net force. I'm going to explain about mass later. Mass is kind of a measure of inertia. A little bit later, I'm going to explain that. This is Newton's second law. If I rewrite this one, F net force equal to mass times acceleration. This is Newton's second law of motion. It's one of the most famous equation in physics. Newton's second law of motion. Let's come back our slide. M is mass of the object, and here you're gonna see the object of an object is quantity. M, the mass of object is quantity. That tells us how much resistance an object has to change in its motion. It's indicated by the second. This is called, this kind of property is called inertia. That is more special term, inertia. Yeah. Inertia important. Inertia message a measure of inertia. Yeah, can see it there. And this resistance to change in the motion is called inertia. Yeah, inertia. The mass is big means all big inertia. Inertia is kind of laziness, hard to move, yeah, hard to move. Yes. Mass is a measurable object inertia, the property that causes it to resist a change in its motion. And unit of force is 1 Newton. Unit of force is 1 Newton. Unit of force is 1 Newton. You're gonna see because y F equal to ma, and then this 1 Newton. That 1 Newton is exactly the same to unit of mass is 1 kilogram. Unit of acceleration is 1 meter per second square. That if I multiply that 1 kilogram times meter per second square is exactly the same to 1 Newton. It's name of physicist. Unit of force is 1 Newton. The smaller mass object experiences a larger acceleration than the large mass object when identical forces are applied to the object. I'm gonna show video, just a demo video. Let me show video. Yeah. Now look at the second law. I'll slide it there. All right. See one example question. A block with the mass of 5 kilogram. Let's see. Mass is m equal to 5 kilogram. 5 kilogram is being pulled across the tabletop by a force 10 Newton, F equal to 10 Newton. 10 Newton. By a string tied to the front end of the block. The table exerts 2 Newton frictional force. Frictional force is 2 Newton. 2 Newton. And what is the acceleration of the block? Acceleration, in order to find acceleration, you need to find F net force divided by mass. But here is F net force, how about F net force? Net force, in this case, this 10 Newton and 2 Newton opposite direction. Then in this case, if I choose this direction, x-axis is positive. This x-axis is positive. And then this one is negative. This one is negative. Negative. Then we can write F minus F, just, 10 minus plus negative 2. We can just write maybe negative 2. Then 10 plus negative 2. F plus F, F plus all the force at 10 plus negative 2 at 8 Newton. 8 Newton will be net force. Then we can find the acceleration. 8 divided by mass of the object is 5 kilogram. The acceleration is 1.6 meter per second squared. Equal to 1.6 meter per second squared. This is answer example 4.21. Now, the next section is about mass and weight. Mass, we a little bit defined kind of a measure of inertia. Mass is defined as the property of matter that determines how much an object resists a change in its motion. Because if a heavy guy, really hard to move, and a small guy, easy to move, right? This is a mass. The greater the mass, the greater the inertia or resistance to change, and the smaller the acceleration provided by a given force. Unit of mass 1 kilogram. Then this if I think of a bowling ball, tennis ball, this is small inertia, but this is big inertia. Then unit of mass is 1 kilogram. 1 kilo. And then what is weight? Weight and mass is sometimes mixed, but mass and weight are different in physics, right? Actually, in daily life, sometimes mixed use mass and weight, but weight and mass is different. Weight is the gravitational force acting on an object, is the weight of the object, right? Because the earth attracts an object, it must have gravitational force. This is weight. W equal to weight. W equal to weight. Always pointing downward direction. This is all two. That weight is equal to mass times acceleration due to gravity. G is acceleration due to gravity. Due to gravity. And on the surface of Earth, G is 9.8 meters per second squared. If we go to the moon, then on the surface of the moon, it will be different, about 1.6 meters per second, much smaller than that, due to actual gravity. Then unit of weight is, of course, 1 Newton, because a weight is a part of force. We have to use unit of the force, right? 1 Newton. Suppose that a woman has a mass of 50 kilo. What is her weight in newtons and pounds? A woman's mass weight, its mass is 50 kilogram. Then weight is equal to mg. That m is 50 kilogram times 9.8 meter per second squared. That is will be 490 Newton. Yeah. Kilogram times meter per second squared equal to Newton. Yeah, that is 490 Newton is the answer of this question. question A. The question B, what about in pounds? That we have to find 409 Newton expressed in pounds. We have to find 1 pound is 4.45 Newton. We're gonna see this 1 pound is 4.45 Newton. We need to have a unit conversion factor. Yeah. Without conversion factor, you cannot solve this one, right? That once you know this 490 Newton equal to 490 Newton times 4.45 Newton. Then 1 pound, right? Then if I Newton cancel that, this will be 490 divided by 4.45 pounds. This once you calculate this one is 110 pounds. 110 pounds. 110 pounds. Yeah, this is 490 Newton in pounds is 110 pounds. Gravitational acceleration is independent of mass. By Newton's second law, the acceleration can be found by dividing the force by the mass, right? Because if I have an object here, its acceleration is A equal to G, right? Then, if I use Newton's second law, F net force equal to ma, right? This is Newton's second law. Then here we can see its acceleration, its acting force, net force is W equal to mg, right? Then the net force, F net force is equal to W. If I use the formula is F W equal to ma, the acceleration will be W over m. But here is weight is V, mg divided by mass. The mass cancel that G, right? The acceleration due to gravity G, right? This one. This we can find, it's acceleration. In this case, for free fall case, there's no any other force acting on the object. We just ignore L resistance. Then acceleration due to gravity doesn't depend on mass, right? Just independent of mass, right? Because mass is cancelled out. Yeah. Only depends on just what kind of planet attracts this one. What kind of planet attracts this one. Then the next section, you're gonna learn Newton's third law. The last law, yeah? Newton's third law. If an object A exerts force on object B, if maybe that's the box there, I push it with my hand. I pushed with my hand. I pushed with the force maybe 100 Newton. Then the box is also pushing me back with the same force 100 Newton, but opposite interaction. This is called action and reaction. This is maybe action, and this is a reaction. Action and reaction pattern all exist. Then here you can rewrite if object A, if I think object A exert a force on object B, object B exert a force on object A. That is equal in magnitude but opposite direction to the force exerted on B. It's 100 Newton, 100 same, but direction is opposite. One is this direction, both this, another is backward direction. Right. This we can write F2 equal to negative F1 vector. If I see direction, if I choose this one, positive X, this X direction, right, that this will be positive 100 Newton. This will be negative 100. Right. And the third law is sometimes referred to as the reaction and action. Reaction and action principle. For every action, there is an equal but opposite reaction. Note that the two forces always act on two different objects. Yeah, it's not the same object. It's one object is object A, one force acting on object A, another force acting on object B, right? It acting on different objects, never on the same object, right? And here is also, if I push the sofa, that here is this one force acting on the sofa, then another force is acting on the hand, right? Like that. And note that the two forces is that Newton's definition of force includes the idea of interaction between objects. You have to see force is just interaction, not just action. Interaction means you're gonna involve two objects interaction. Yeah. So one action and another is a reaction. Yeah. Action and reaction pair always simultaneously appear simultaneously, removed like that. Yeah. This is action and reaction. Okay, see, there's some, I think, let me show some video to the solution. The solution. need to explain this one. Right. Let me move back to our slide here, and then here, normal person weight act on the book resting on a table. Yeah, she explained, and here is if I think the book, it has weight. It's because the earth attracted the book. It's yeah, M W. W acting on downward direction. Then also because the book is attracted by the earth, and the earth is also attracted by the book with the same force, just opposite interaction. Same in magnetic, but opposite interaction. And also normal person is acting on the book. This should be maybe right. Should be this direction. This is very, but if I write this book right there, normal person is over the direction that is support the book. Otherwise, book is just the real ball, but is not, because the table is support the book. There's an n. If I think this is right axis like n minus w, n is positive, w is minus equal to 0, because f network is equal to n a. But in this case, not moving, acceleration is 0. That is equal to 0. That is n minus w equal to 0. Then normal force equal to weight. Right. This normal force is also there is a reaction pair, because this book is pushing the upward direction with force, and then also the book is also pressing the table with the same force, and but in opposite direction, negative, like that. Yeah, you can write this way. And the second force acting on the book is upward force exerted on the book by the table. This force is called normal force. You have to see normal force. Where the word normal means perpendicular. Normal means in physics, normal is just perpendicular, not abnormal. Normal just perpendicular. Perpendicular to what? Perpendicular to the table, just the contact surface. This surface is perpendicular. The force acting on the object is, but that is perpendicular. And here is by have this spring, an uncompressed spring and the same spring supporting a book. The compressed spring exerts an upward force on the book, right? Because here is gravity here, weight here, but even weight is not falling down because there is the spring force like that. This maybe spring is pressing upwards. It's like it can be regarded as a normal force. Then is because book is pressed upward direction, then this book is also pressed to press the spring downward direction, and same magnet but opposite direction like that. Right. Gonna see what force causes the car to accelerate. The engine drives either the rear or front axle of the car, which causes the tires to rotate. Tire rotate. The tires in turn push against the road surface through the force of friction F between the tires and the road. Because of friction, this is pushing, and the flow is backward direction. Pushing this, but oppositely, this road is also asphalt road is also pushing just backward. The reaction force is negative. This force make this car is forward direction, right? If maybe there is no friction, this is ice, the car cannot move forward because there is no friction. According to Newton's third law, the road must then push against the tires with an equal but oppositely directed force, negative F. This external force causes the car to accelerate. It's working people are the same. Human working is like that. It's maybe here my what here, but I put push it backward direction. I apply this force to the ground, and then also the ground gives me reaction force, this direction, negative force. Because this force, I move forward direction, right? And the last section, application of Newton's laws. Forces involved in moving a chair. The force of gravity, W, is acting on their downward direction due to interaction with the earth. The other force, the upward normal force, is because there is a blow is pushing upward. This is normal force exerted by the blow due to compression of the blow. The force exerted by the hand of the person pushing P. The frictional force F is opposite here, exerted by the blow. Then what about the skydiver? Does the skydiver continue to accelerate? You know, skydiver is going downward direction, but the force of air resistance acting on a skydiver increases as the velocity increases. You know, in this case, R is initially small. If no motion, no air resistance, but if moving, this R is small, but V is small velocity. But velocity will increase because of this gravity that keep accelerating, then velocity is huge. In this case, the resistance is increasing like a longer arrow, and then also again increase the keep accelerating. Then eventually this force and this force is same. That W, if I think this direction is y-axis, that W is positive. W, R is negative, minus equal to, it means MA, F equal to F, this F also. It means acceleration means no acceleration. Acceleration is we defined as a change in velocity. Then it means there is no change in velocity. It means velocity is constant. V is equal to constant. That at this point, this moment, then its speed will be constant. Keep moving same speed. At times, if resistance and air resistance and gravity same, then this velocity called terminal velocity. Terminal velocity. Then final velocity is there. As the velocity continues to increase, the resistive force reaches a value equal in size to the gravitational force. The net force is then zero. Skydiver stops acceleration. She has reached terminal velocity, and from there on, she moves downward with constant velocity, about terminal velocity 100 to 110 miles per hour. Still fast, right? 100. This is about really fast. Really careful, right? But eventually, she needs to open the parachute. Yeah, then maybe the speed will decrease. In this speed, if she hit the she will be killed, right? But I think she needs to open the parachute. Parachute that provide more air resistance that make decelerate. The speed will slow down. What happens when a ball is thrown? Ball is thrown and it keeps moving, but in this case, only gravity acting on there, like here. The air resistance there. Air resistance keep opposite direction against the motion. Motion is this direction, gravity same direction, same, but air resistance keep like there, but change direction. Three force act on a thrown ball. The initial push P applied there. That there's initially there's velocity V equal to 0. Then resistance is also 0 because resistance depends on maybe proportional to the velocity. Maybe sometimes proportional square velocity depends on speed. Initial push P and the weight and air resistance are vector. I'm gonna solve this problem last one. Two connected cards are pulled across the floor under the influence of a force of 36 Newton applied by a string. The board cart and its contents have a mass of 10 kilograms. And this is M1 equal to 10 kilograms. M1 is 10 kilograms. 10 kilograms. And the second cart and contents have 8 kilograms. M2 equal to 8 kilograms. what the accelerators two cards? What is the net force acting on the each card? If I see like this one, this is M2, like that. I apply the force F, then there is maybe normal force applied here. Then gravity is M1 times G, right? Gravity. And then this, there's together there, this is putting the tension force there, tension force. Then also here is normal force is maybe N1, N2, M2G there. This is gravity. Then I think there is no friction. Yeah, there's no mention of friction. There's no friction. Assuming friction, it will not react. Negligible, no friction. Then also because M1 is pulled by M2, then M1 also pull M2 too. This same force. This action and reaction, but this is opposite direction. This force same magnitude but opposite direction. This is going to this direction, this is going to this direction. Then we chose this direction is the x-axis, right? Then we're gonna see acceleration is the same because this is connected together. The acceleration must be same, right? If you these two objects move that connected, this is 3 meters per second. This also 3 meters per second, the same moving together. Then two objects connected each other. The acceleration will be same. Then we can use maybe Newton's second law. A is F for M1. Newton's second law is F minus T, because T is opposite. We chose this is positive direction. F is positive. T is negative because opposite direction. Equal to this is net force, right? Left hand side net force. Net force will be like that. Right hand side M1A. The for M2, if I write equation motion, the M2 is the force acting on objects. M2 is there is only tension force there. T is positive direction. There's not any other force there. Equal to M2A, right? Then we can add 1, 2. Equation 1 plus 2 will be what will happen there? If I add together, negative positive will be cancelled out. That will be F minus T plus T. Left hand side, this is will cancel out. Right hand side M1A plus M2A. That this will be factorized because A is common, but M1 plus M2A. Then we can write A will be F over M1 plus M2. F is the force is 36 Newton. The mass of the M1 is 10 kilogram. Mass of N2 is 8 kilogram. That this will be 36 over 18. It will be 2 meters per second. This is answer of question A. Acceleration is 2 meters per second. Yeah, same acceleration. This and this acceleration same. Question B. Net force acting on M1, and then how to find F1, F net force 1. That is actually F minus T, but we don't know T anyway. This one M1 times A. This will be M1 is mass is 10 kilogram times acceleration 2 is 20 Newton. 20 Newton. Then object M2, object 2. This one F net 2. F net 2 is that is T. That is M2 times A. M2 is 8 kilowatt times 2. That is 16 Newton. 16 Newton. Yeah. Like that. This is answer question A, question B. That's all. All right. Yeah. you have any questions, send me email. And yeah, this is the chapter 4, Newton's law of no laws of motion. Yes, there are 3 laws. First law is the law of inertia. The second law is F equal to ma. The third law is about action and reaction. F1 equal to negative F2 vector. Yeah. Then one object, if I apply object A, apply force with F on object B, then object B also apply force on object A with the same in magnitude but opposite direction. Yeah. So let's have a good day. Bye.